Hey everyone, good afternoon. My name is Abhay. I work at AudioShake. And who's heard of AudioShake by round of applause? Yeah, all right. And who's not heard of AudioShake? Make some noise. All right. All right. The rest of you figure something out. Okay. So this is the only audio talk for the evening or for the couple of days that we have video guys here because, audio is also important because, without audio, the video would just be a bunch of images. So here we are. Okay. All right. No, but this is important. So yeah, what do we do? AudioShake. We basically are we make sound usable for humans and machines through audio separation, splitting source sound into component parts. So what does that mean? It means that we're trying to basically take out individual components of an audio source. So here's how this is done. This is called a spectrogram, which is basically like an X-ray of a audio system or of an audio signal. And what this is showing us is a frequency versus timestamp of the image. And what our traditional noise suppression models do is that they take out noise from the signal. And what we do is it's source separation, which is technically a little different. So in noise suppression, what happens is that you can see in this image that when we take out the noise, you can see that it's taking out the noise, but there's still some, fidelity issues because it's not able to isolate each of the individual stems. So what happens in source separation is that we're able to identify each of the various sources within an audio signal. So you would have speaker, crowd, speaker two, and music. And what the AudioShake model does is that we can target specific sections of this and then isolate that. So one of the examples that I'm going to show you here is, dialogue RT, where we're able to separate one dialogue stem and then the rest is just background noise. So that's a quick and easy way of getting at least one dialogue stem. And here we are. So how does this work at a high level? We have an audio source in, and you have a spectrogram. That spectrogram's then spliced in our model based on a transformer model. And then once that processing is done, we have the stems that are output as part of that model. So each target is rendered back to the audio, and then they're summed and rebuilt in the mix. So why do we need to do this? It's multiple reasons, and I'll talk about that as we progress. So here are some workflow integrations that we've explored. One is, this is a traditional OTT workflow where you have, in a sports broadcast, you probably have phase one where you have a capture of the source content, and then you have all that source content is sent to a broadcast center. And those are the two places that we're trying to actively have POCs for AudioShake, where we can separate different types of source audio, and that's where the dialogue RT product comes in. And then there's also a phase 6 where we have the batch API process of processing massive amounts of video and audio so that we can separate the audio and then restem them. So those are some of the areas that we've been exploring in the workflow itself. And here's the real problem, right? Like you have broadcast audio is extremely messy because you have multiple source points. You have multiple commentators, you've got different languages that need to be supported. Stadium speakers bleed in, and then you have field effects like crowd roars, arena music, field microphones. All of that has to be mixed into a tangled feed. And because of that, the impact is that speakers get mixed up, captioning and subtitles can be faulty at times. Clips get blocked online because sometimes music can bleed into the dialogue of the commentators from the venue itself. And you don't necessarily have the rights to broadcast that music once you encode that content. And then there can be an issue where you have profanity and then you have to mute the whole broadcast. So, those are some of the impacts that we are seeing in the field. Now, traditional approaches to audio cleanup, what does that imply? This is noise suppression, which we talked about. It can be used, but it constantly requires manual intervention. And then music removal currently at the moment has no specific fix that we're looking at. So what broadcast A1s do is that they swap out the commercial music for library music. So yeah, and here's some of the other challenges I was talking about, where we have noisy speech inputs, profanity, and commercial background music. So we've solved some parts of this in post-production because we have a larger window of sampling. So we focus on speech separation, isolating specific sounds in a broadcast, and then also music detection and removal. So we've been able to do this for post-production. So the challenge, the way it's done for post-production in music is that we have this workflow where we detect the music, music is removed, and it can be remixed with another track. And then you can also isolate music with a content recognition system and also have music metadata attached. So yeah, what do we do in the broadcast latency problem? So the issue right now is that there's broadcast is very, very complicated, right? And then you have to be as quick as possible to maximize your production, right? So we came up with Dialog RT, where we can get clean dialogue separation within 11 milliseconds with the AudioShake subsystem. And that gives us greater control over downstream systems like captioning, ASR, or immersive mixes. The way this works is that we have the system just identifying dialogue and then taking that out, and everything else is discarded as part of a background stem. So here are some trade-offs, right? Like how does this actually work? So you can see here that Dialog RT derived dialogue is within 11 milliseconds, and it's well above the broadcast use case, broadcast usable use case. And here's the post-production version. And the challenge here is that you're pretty much racing against the physics of the entire system. So as part of the arrangement, we've been able to benchmark on some NVIDIA platforms, and what we've seen is that we've been able to reach a pretty good latency number based on Dialog RT. And then some of the cases that we're thinking about is there's what does this mean? So for post-production proper, it's 3 seconds end to end, but in the case of Dialog RT, it's 11 milliseconds, so it's pretty quick. And what you do get is a good isolation of speech, but in the case of post, you get other stems as well. So yeah, this is something that we've been looking at. And then in terms of ways to integrate, we have a cloud API and an on-device SDK that's available. So yeah, just zooming out a little bit, how does this work? So you have an audio signal that's sampled in the system, 48K or 48,000 times a second, and then it creates these buffers of 512 and 512 sample size, and then that's fed into the model, and the model consumes the chunks, and what happens is you get a clean output of 3 different stems. So that's at a very high level of what's happening. And inside the system itself, we are looking at 11 milliseconds processing windows, and that does not include the I/O effects, which can add some level of latency to the overall system. So our goal is to try and squeeze as much as we can in terms of getting the right dialogue out of the system. And at the moment, we're able to get to 11 milliseconds processing. And here's a real-time versus fixed deadline. So the way it works is that we process 11 milliseconds of buffer size at a time, and then once that's filled, then we have the next buffer ingested in the workflow. All right, so broadcast latency takes both, it's a combination of figuring out a couple of things, right? One, if you had to take 2 takeaways from this presentation, it would be this, right? How do we get Dialog RT to work, and what is the next step? So we get Dialog RT to work by having optimizations done on the algorithmic level, and then there's a second line of optimizations done on the platform itself, which is the NVIDIA platforms. So the coupling effect of those 2 processes leads to a pretty good output of the dialogue. So that's how we've been able to get these 11 millisecond numbers. And the good news is that we've been able to also process 16 different streams and parallelize the entire process on the NVIDIA Spark. And we have some benchmarking data that we've developed over the last few weeks. So this is all very early stuff. It's still work in progress. All right. But yeah, we're pretty happy with the results so far. And yeah, there's still bigger challenges for us to figure out, which is, how do we apply the same approach to music what happens in the case of, because right now it's just, it's a fairly complicated problem to have music also be at the in the low latency model. Profanity detection is something that we're working on. Drone effects and isolation, that's a big one because, it's a fairly complicated sound that is got a varying frequency profile. So mechanical effects is what we're looking at in terms of developing a model for that. And yeah, we're in active POCs with multiple customers. So would love to. I don't know if this is going to play, but
rollers, and Lindsey Vonn makes it to the finish line.
Across the finish line. Mere 4 tenths off the pace for Lindsey Vonn.
Flying over these finishing rollers, and Lindsey Vonn makes it to the finish line.
all right. So yeah, that is a work in progress with the drone noise removal. I think the challenge with drone noise is that it's a moving target, right? So there's a fair amount of work that needs to be done in training the audio data sets to make sure that we have a good map of what the drone noise represents. And there's different kinds of drones. Each of them have their own frequency responses. So training the algorithms is going to be crucial for mapping out as many use cases as possible. But yeah, those are some of the use cases we're thinking about. Yeah. Yeah. Thank you so much.